Welcome to part 6 of the linear and nonlinear relationships topic. The last few lessons we've been looking at parabolas. Today we're going to have a look at exponentials. So let's get started. Parabolas are of the form y equals x squared, but what happens if we swap the x and the 2 around? So instead of y equals x squared, let's make it y equals 2 to the x. Now we have a fixed number as our base. Remember, this is the base. And our variable x is the power. Now power is how we most often describe that number there. But it can be a power or an index or an exponent, hence exponential equations. So, like we did last time, let's draw up a table of values. We'll plug in some x values, see what we get for y, and then we'll see what the graph looks like. Okay, let's start off with the positive values of x. So we'll start with x equals 1. When we substitute x equals 1 into our equation, we get y equals 2 to the power of 1. So that's just 2. What about when x equals 2, 3, and 4? What do we get? Y equals 2 squared, that's 4. Y equals 2 cubed, that's 8. And y equals 2 to the power of 4, that's 16. What happens when we take y equals 0? X equals 0, sorry. Remember, anything to the power of 0 is just 1. What about negative numbers? Let's try negative 1, negative 2. Here we have to remember our negative index laws. 2 to the power of minus 1 can be written as 1 over 2 to the power of 1, or just 1/2. And 2 to the power of minus 2 can be written as 1 over 2 squared, or 1/4. So what we notice is that even when we go into the negative x values, our y values still stay positive. Even though they're getting smaller and smaller, they still stay positive. So let's take these points and we'll graph them now on an xy axis. Because we only have positive values of y, we only need to focus on the part of the axis above the x-axis. Alright, let's start with our y-intercept. So our point 0, 1 is right here. Then we have the point 1, 2, the point 2, 4, point 3, 8, and 4, 16 all the way up here. So you can see it rises very quickly. For our negative values of x, we have negative 1/2, and negative 2 1/4. So getting very close to the x-axis. But the further we go to the left, the smaller it will get, but it will never get to 0. Let's join these points now with a smooth curve. Pretty close to smooth. Let's make a few notes now on our graph from what we notice. While we have our base as 2, exponentials could have any base. We'll call that a. The first thing is that as our x values increase from left to right, our curve increases. So we can write the curve increases as the x values increase. Next, if we just focus on the positive values of x, just here, the curve not only increases, but increases very steeply. A key feature of exponential graphs. So there is a steep rise for positive values of x. When we contrast that to the negative values of x, we see that our curve flattens out. So as we head this way, our curve becomes almost flat. Not quite, it never will be flat, but almost flat. So our curve flattens out for negative values of x. Now, as it flattens out when we head towards negative infinity, we noticed how the curve got closer and closer to the x-axis, but it never actually reaches it. Whenever we have this occurring with graphs, we use the word asymptote. So the x-axis, or the line y equals 0, is an asymptote. This is a line which the graph gets closer and closer to, but never actually touches. So asymptote, this is how you spell it. And that's as x approaches negative infinity. So as we go off this way towards negative infinity. The final feature, it's always good to note for any graph, any intercepts. And regardless of what the base is, the y-intercept of y equals a to the x will always be 0, 1. Remember, anything to the power of 0 is 1. So there are some key features of our standard exponential graph, y equals a to the x. Let's go and have a look at Desmos now and see how exponential graphs can change as we change some of the variables. Let's start with y equals 2 to the x, the graph that we drew before. But what happens if we change the sign of our power? So instead of y equals 2 to the power of positive x, what happens when it's a minus? We notice that it flips about the y-axis, because every value of x that was positive is now negative and vice versa. So changing the sign of the power flips our graph, or mirrors it about the y-axis. What about if we put a minus out front of the whole thing? This takes every y value that was positive and makes it negative now. And since an entire exponential graph lies above the x-axis, now everything lies below the x-axis. So there we go. It's been flipped or mirrored about the x-axis whenever we put a minus out the front. Alright. Now we've been using a base of 2, but we could use any number. What happens if we increase the base? Well, if we increase the base, the curve gets steeper. Alright, 3 squared is 9 compared to 2 squared. And so 3 squared is 9. So I get this point here. At 3, 9. As compared to 2 squared, which is 4. So as we increase the base, our curve gets steeper. Now, just like we looked at with parabolas, we can translate our graph by adding on a value. So let's start with y equals 2 to the x, but then we'll add on 4. See, we've moved our entire graph up by 4. And what's interesting to note here is that while in our original graph we had an asymptote of x equals 0, now we have an asymptote at x equals 4. Sorry, y equals 4. So this green line here is an asymptote for our blue graph. Our blue graph of y equals 2 to the x plus 4, as it goes down towards the left and approaches negative infinity, it will never touch the green graph. We can zoom in and it gets really close, but it never actually touches. See, as we go down further and further towards negative infinity, it gets closer and closer, but never actually touches, always getting smaller and smaller, the gap between them. Right, we'll zoom back out. So if we translate a graph by adding on or subtracting some number, it's important to note that the asymptote moves with the graph as well. Let's have a look at if we subtract 4. We've now moved the graph down 4 spots. So the y-intercept that was previously at 0, 1 is now down at -3. And the asymptote that was previously at 0 is now at -4. So here it is in orange. Okay, let's go back. So we have drawn our standard exponential, y equals a to the x. Let's now draw some of our other standard exponential curves. Let's start with y equals a to the minus x. Remember, in Desmos, when we changed the sign of the power, what we got was a flip about the y-axis. So instead of our graph rising from left to right, it decreases. So that's our basic shape for y equals a to the minus x. If we instead made the entire expression negative, so y equals negative a to the x, we got a flip about the x-axis. So now the entire graph fell below the x-axis. What would happen if we made the entire expression and the power negative? So a negative here and a negative here. Well, that would flip it both ways. Being mirrored twice about the x-axis and the y-axis would give us a curve that looks like this. Let me have a go at drawing that again, sorry. That's a little bit better. Hopefully you get the idea. And finally, if we added or subtracted some value at the end, so let's go back to the standard exponential, y equals a to the x, but then we add some value k. That takes our graph that previously had an asymptote at y equals 0 and moves our asymptote up by k places. So this is the line y equals k. So it might be moved up by 2 or 3 or 4. And now we can draw our exponential. Alright, so that's our lesson on exponentials. Good luck with the questions.